Hey there, it's Max, and I've got a doozy of a video for you today. Last year at the Spokane Cyber Cup, we did a challenge that required students to actually touch things. And having something that they could physically hack just blew their minds. And it blew my mind at the ICS, or Industrial Control Systems CTF, the last couple of years too. This last year, we had an airline ticket scanner that we made. This is just an Arduino with a QR code scanner, a display, an Arduino in it, and then Max Arnold was very nice and 3D printed those really nice boxes and soldered everything for us. And students just loved this challenge. For it, you had to modify your airline ticket, and Yasmin printed out like pretty realistic looking airline tickets. This challenge was cool last year, but I've got one cooked up that I think is even better than the airline challenge. It takes this whole concept of touching things and seeing stuff physically happen to another level. This year, we've got an NFC card challenge. This NFC card has information that is trying to mock their student card. It has like Bulldog bucks kind of thing, like it has money. It has their administrative role. It talks about what doors they have access to. I think this is super cool. So I've got a different setup here that we're gonna be able to see. I've got the I got the source code here. I've got the challenge information, and then I've also got my phone set up for a capture. So let's go through the challenges. I think it's a good little teaser for the year. So the first challenge is just getting them to download the NFC app. One thing that's really nice about NFC is that most smartphones nowadays support it. And the NFC Tools app is on both the iOS and Android App Store and has everything required for free to complete these challenges, which is pretty cool. If students don't have smartphones, they can borrow one of mine. I don't really care. We'll make it work. So for this first challenge, all you have to do is just scan the QR code or scan the NFC card and read the flag. So if we go here, we click read and we scan it, we can see that there's various information on it. And down at the bottom here, you can see that there is a flag. The best is yet to come. The other fields are pretty simple, and I will show what those are in a second. So if you go back here, I actually need to reflash this. So might as well just show this off. So this has a little CLI that the students will interact with. There's different options. The first one is just displaying the card. The second one is paying a parking ticket, because I got a lot back when I was in college. The third one is just checking the flag, see if you solve something. And the fourth one is reflashing the base image just in case you corrupted it. And in this case, I've already solved some of them from a previous run, so I need to reflash it. So this just reflashes the card for us. And now if we do display, we can see the information. So even though we can't actually see what these fields mean here, we can infer and figure out what this is based upon the information on the screen. So we have purple cobras as the team name, school is just Spokane, the door access is an array, this card role is a student, and then the cash amount here is how much money is on their card. Ignore this. This shouldn't be there. I was debugging something and I forgot to remove it. Wherever that's at. Yes, here is my debugging code. We will remove that. We will look at some code later, though. So we already solved one challenge. What's the next challenge? It's just getting the UID of the card. Now, this seems kind of bland and boring, but this is actually really important for the fourth challenge, and you'll see why in a moment. For this, we're probably going to have to scan every single card we give out to students. That's fine, because we need to flash them anyway. And then we'll put this in a huge regex on CTFT so students can submit their UUID. So if we go here, we would need to reflash or read the reflashed one. We can see that I'm not sharing my screen. Dang it. We can see that the serial number here is the flag. So the serial number, UID, same thing. Probably should have changed the name of that, but that's okay. So this is the next flag. The next one I think is pretty fun. So if we see here, these are called NDEF records. And these records are a mechanism of storing the information on the NFC card where it's easy to pull off and there's a recognized medium to do that. There's a standard to say. But that's not how this thing actually stores information. So for the next challenge, the students need to read the raw memory and try to see if they can find the flag. If we look here, it says we need to read pages hex 70 and onwards in order to get the flag. If we go back to our phone, and there is an option called read/edit memory, we can see that there's a bunch of values, but we'll reach a point where we've written all the data we need. And we just have a bunch of zeros. But if you go all the way to 70, particularly if you look at 6F, we can see 6F is still zeros, but 70 has information. It's 53, 43, 36, 7B. And I don't remember what those are ASCII off the top of my head, but if I had to gander, it's probably an SC6. You might guess. Yeah, 36. I know hex 30 is 0, so hex 36 is probably 6. So if you decode the hex and turn it into ASCII from address 30 to 35, you'll get the flag. I think it's pretty cool. This allows students to dive a little bit deeper than just looking at records. They actually have to understand how stuff is formatted, get a little bit in the lower level of NFC. I think it's really cool. Go back to the screen, we can see what the next challenge is. This is probably my favorite challenge. So I was actually reading a blog post where some guy had a business card, and these business cards he bought or had NFC on them so people could scan them. The problem though is in order to write the URL on the NFC cards, you had to pay $70 for this subscription to use this app. And the guy said, screw that, I don't want to do that. So he reverse engineered the app and realized that this was locked, but he figured out what the password was. So this is kind of a real thing, having to figure out the password for this. So students are going to have to read a little bit of Python code. Maybe there's another way to do it. Could guess some entries. Could get some hints that way too. But the intended way is to look at the code a little bit. So if we look at the code for write card, it needs to authenticate. And when we call handle write, when it authenticates with password, it's calling connection with the password UUID. And if we look at the description for this, the passphrase is what we're passing in. The passphrase UUID is literally just giving the UID of the card. Now, this seems kind of weird, but this is actually a pretty realistic thing. How else do you get unique information per card? You know, a big issue with routers, for instance, was that everything would have default credentials to begin with, and people wouldn't change them. But on the flip side, what if you need something unique? You need something that's easy to get. One thing that's easy to get is UUID. On IoT devices, I've seen lots of things use like the MAC address or the serial number, various other things for secret information. It's a fairly common pattern. So I thought throwing that in here was fun. It's somewhat guessable if they're not very good at reading code. So we know the UID of this. It's easy to read, it's in our app, so therefore we know the passcode. If we go back to our screen, we can call read once again. We can scan this, and we can copy the serial number. In the other section, there is a remove password function. So if we call that, and we scan our card again, it's successful, which means that we did erase the password. If we read the NFC card one more time, you'll notice that the protected by password is now set to no, when before it was set to yes. So I think that's a pretty cool feature. We're able to just remove the password using this. For the challenge itself, you can't just say, hey, look, I removed the password. Look at me for a flag. Might be able to. Actually, no, I'm thinking about it, you probably could. But I think getting the students in the habit of writing is also cool. So we have the student role and the admin role. We want the student to become an admin. And if we look at the card data, we can see that their student role is just a student. So if we go back to our phone, we can start to write to it. So this is the one bummer. I have the paid version of the app because I was testing this and using it a lot. But you can also there's a workaround for this in the unpaid app or the free version. So in the paid version, if I go to write and I do more options, I can do, do I need to clear this? I think I need to clear this first because I was using it earlier. But you can import all of your information from this and then write to it, but you can also just click write record and do every option that they need to do. But just for the sake of time and me being lazy, I'm just gonna import it, and now we have the ability to write. So if we go here and we change the student to admin, and then we write to it. Now if we go back to our CLI, to the scanner, we can now see that our role is now admin. So we're able to successfully edit the card. And if we do option 3, it will give us the flag. So I don't want people cheating off each other, so it shows the flag very briefly, and then it clears the screen. So students will probably need to take a picture of that, but that's okay. Once you have it solved, it's pretty easy to solve it. Again, just ask for it one more time. So the next challenge is editing the money. Now, you probably don't remember seeing a money field on the records, but if we look at this on the scanner, we can see that there is indeed a cash money amount. This amount and this value corresponds to this entry on the phone. We can see that there's a number and there's a long string of characters. This is a SHA-256 hashing function of the number itself. The idea is that it acts as a proof of a checksum of sorts to make sure that this thing isn't corrupted. But it's also, in reality, it's not security, but people think it is. Like I've seen people using hashes and digital signatures and various other things in the wrong places. So we need to substitute this value, the SHA-256 hash of that value. And it's not too hard. Here, I just have this pulled up, and I need to set the value to be larger than 10,000. iOS has this nifty feature where I can just copy it from my phone. So I copied that into the app. I'm going to copy that one into the app. We'll go back to the phone so you can see that now. So we have those values in there. I just copied the hash and the value. And we do OK. We do write. And now we can go back to the CLI and we can display the card. You'll notice that the number is much larger. And if we ask for the flag, it will now say that we need to put our hands up because we're under arrest for stealing money. It gives you the flag. There's also a couple of other ways to figure out what's going on here with the numbers, though, besides just reading the source code. The first one is, or the next one is, if we look at the options, there is a pay parking ticket option. I paid a lot of parking tickets in college, so I thought that'd be funny. If we click that, we'll right to the page. And if we look at this one again, the amount is the cash money is changed. So if we go back to the card and read the information, once again, the SHA hash here has also changed alongside the number. So this is a good way to demonstrate, this value is somewhat related to this hash, even though the first one is the number, we don't know what the second one is. And by knowledge and knowing stuff, you could figure that as a SHA-256 hash. A lot of times you can just look at a hashing function based upon the characters and the length, figure out what it is. So after that, there's one more way we can actually figure this out. If we change this to have an incorrect hash. So I need to go back to write. And in here, and say we just put a bunch of bad stuff in there. We wrote that. And then you tried to pay. It actually gives you different information. In the card data screen, it tells you corrupted the money amount. If you try to pay, it won't let you. And the error message says SHA-256 hash does not match balance. So there's a couple different ways to solve this depending on different strategies. If you'd like to read source code, you can do that. If you just like black box reverse engineering, you can also do that, which is cool. So the final challenge I think is also pretty fun. To be fair and biased, I think all these challenges are really fun. This is door access. So it says that the door access is purely stored as a number, and it wants you to try to figure out the format of it. And in order to solve this, you need to set it up so that you only have access to doors 4 and 11. If we look at the CLI and you look at the card data, you'll notice that it gives you a list of what doors you have access to. In this case, it's 0, 1, 4, 6, 8, 10. However, if we look at the raw card data again, there's no things that have that array in there. What's going on here? So, by process of elimination, it's probably this one, because everything else is being displayed there. So, if we change this from a 6 to a 4, and write this, then go back to read it. Remember, I'll copy this here so we can see it still. Ignore that. I don't like that challenge idea. So we go back to the CLI and we display the card data. You'll notice that what we have access to actually changes. Instead of having 0, 1, 4, 6, 8, 10, now it has 2, 4, 6, 8, 10. Why is that? That's weird. So there is a trick to this. And you can either do this by dynamic testing or by looking at the source code. But this ends up being a bitmap. So for instance, if we do 2 times 0 plus 2 times 1 plus 2 times, or exponent 4 plus 2, 6 plus 2 times 8 plus 2 times 10, that's the exact number we started with in the first place. So with a bitmap, every bit represents a particular Boolean flag. So bit 0 represents door 0. Bit 1 represents door 1. So if we want to set that just doors 4 and 11 like we say, we just needed 2 times 4 plus 2 times 11, and we get 2064. So if we go back to it and we write, and we hope I wasn't sharing my screen there. So I changed the text to be 264 now. We write that, and if we go back to the CLI and we do check flag, it has to go through all of them again. Let's go through all of the options again. So it's 3 doors down is a kryptonite. So that's what that challenge is right there. It's just modifying the bit flags. If we look at read card, we can also see this in here. If we go to door access check, you can see that it's doing some bitwise math. It's making sure it's not all ones, because I didn't want that to be an easy solution. It's shifting them over by the door number, and then it's adding it by 1. And if that's equal to 1, so we've shifted everything over and done a bit mask of 1, so it should only be the last bit that's still there. So checking that is equal to 1 works pretty well. And then when it calls gen list, which is what gets stored, it's just taking the number, and if the and of 1 is equal to 1 here, then it appends it as part of that list. So theoretically, students could figure it out by messing around with it or reading the source code, but I think it's good either way. So that's a sneak peek to this challenge. We're gonna have this in a separate room, and somebody's gonna have to kind of be with the students at all times, helping with it. But really excited for this year's event. Excited to have you guys as coaches. Give me the best one yet. Thanks, everybody.